Okay, so hello everyone. Welcome to lecture 11 already. We are in the last third of the course of your introduction for quantum optics. And let me remind you where we are. So we are right now in a very special chapter because it's what is for me kind of the most characteristic feature of the field of quantum optics, which is that we deal with open quantum systems in a very natural way. And then a lot of the techniques of open quantum systems have been developed by people working in quantum optical systems. And this is actually the field I work in the most. So let me remind you just a little bit of where or what we did. So essentially, the theory of open quantum systems means that instead of working with a system that is described just by a Hamiltonian, we have a system that it's what we call open in the sense that it is interacting with another system that we call environment. And it's typically much, much bigger than the system itself, and over which we have no control, okay? And we are not monitoring it. So essentially we have the system that we would like to have closed, or maybe not, but typically we want it closed, like if we are doing a quantum computer or whatever, we want the quantum computer isolated. But then we cannot we cannot help but having a little bit of interaction with degrees of freedom that we are not taking into account in the experiment. And therefore, we have to develop a theory for this system that includes this kind of interaction with an environment. So what I told you is that the goal of the chapter is essentially to find the dynamics of the system alone, what we call the reduced dynamics of the system. And we can proceed in two ways, either with the Heisenberg picture or with the Schrödinger picture. And each of these pictures has its own interesting features. And in particular, the kind of equations that we will find for the system are of two very different types. One is called quantum Langevin equations, and is what we will see today. And the other one is master equations that we will maybe start today. So essentially, I told you that we will start with a very simple example, and then we will kind of generalize it a bit more, the theory. So, and the simple example is just that of an open cavity, okay? So the first thing that we did was developing a model for the open cavity. And in particular, it's always the situation in which the whole system, including the environment, plus the subsystem we are interested in, form a closed system. So everything is described by a Hamiltonian. So then the first thing that we have to do is finding a description of the environment associated to an open cavity and to the interaction between the cavity and the environment. So what I showed you is that essentially the field outside the cavity, okay, so the field, let's say in free space outside the cavity, can be described with an electromagnetic field composed of a continuous set of harmonic oscillators. And in particular, we made this specific form, this specific form in terms of annihilation and creation operators, but that form a continuous set. And in particular, you have these commutation relations, which are the generalization of the commutation, the canonical commutation relations in the discrete case that we already know. So they are the generalization of that to a continuous field or a continuous set of operators. So then once we have a model for that, and by the way, we did the theory focusing only on one mode of the cavity, and today we will discuss what happens when we include more modes. So we focus on one mode of frequency omega c with annihilation and creation operators A and A dagger. So essentially, when it comes to modeling the Hamiltonian of the system, we will then have a free term or free parts in the Hamiltonian that correspond to the free Hamiltonian of the cavity, which is just the harmonic oscillator Hamiltonian, A dagger A, and then a free Hamiltonian for the external modes, which it's of the same form. We have to sum over all the set of modes, so in this case, integrate, and then we will have the B dagger B of each of the modes outside the cavity. And then we have to introduce an interaction between the system and the environment. And then in this case, it's very simple because just out of many arguments that I gave you, at the end of the day, the Hamiltonian, we can write it in this way, in which essentially we are saying that photons can tunnel in and out of the cavity, okay, at some rates that are related to this coupling G of omega, that in principle we can allow it to depend on the frequency. So different frequencies can tunnel at different rates. And then essentially we see that what we are including here is this single photon tunneling, in which you can annihilate one photon of the cavity and create one photon outside the cavity, and that would be tunneling out, and then the Hermitian conjugate process is tunneling in. So, however, we can simplify a lot this situation, at least for optical cavities with good mirrors, because the argument I gave you is as follows. It's simply that essentially the tunneling, okay, so this tunneling parameter G is essentially proportional, or it has some kind of proportionality to the transmissivity of the mirror. So essentially it depends just on the transmissivity on the mirror. That's the most important component. And then if we have a very good mirror, okay, then this parameter will be small, and this Hamiltonian, we can consider it as an interaction. On the other hand, energy conservation tells us that we will not be able to tunnel outside the cavity to arbitrary frequencies. We will always, as we have seen in previous chapters, we will always, by energy conservation, be restricted to photons inside the cavity tunneling outside to nearby frequencies to the cavity resonance. So in particular, what I said is that essentially out of all the frequencies outside the cavity that are infinite and form a continuum and so on, essentially only the frequencies that are around the cavity frequency are the ones that we expect that will contribute. Any other frequency will be kind of canceled. And therefore, in that situation, taking into account that mirrors in an experiment depend very softly on the frequency, okay? I think that otherwise it would be very weird that suddenly you are working with a laser at one frequency, the transmissivity or the reflectivity of the cavity of the mirrors of the cavity is very good, and then suddenly you just move it a little bit and then it's very bad. That would make it impossible to do experiments with such a sensitive system. So then in general, we can say that around the cavity frequency, okay, in particular around the cavity frequency, we can kind of approximate this coupling of omega by just frequency independent coupling that depends only on the cavity frequency. And and we were calling just the square root of gamma over pi, and you will understand why I call it the square root of gamma over pi today. And then in the interval of frequencies of omega c minus omega minus gamma and omega c plus gamma, we can essentially make this approximation in which the coupling is flat. It doesn't depend on the frequency. But moreover, in order to simplify derivations, as you will see today, we can also introduce some kind of fictitious modes with negative frequencies. Of course, that doesn't make any sense. Frequencies are not negative. But we can mathematically introduce these fictitious modes, okay? And then extend the integrations instead of from 0 to infinity, from minus infinity to plus infinity. And this, as you will see, this simplifies everything. And of course, the negative modes will not contribute because, as I have said, and we will prove today, only modes around the cavity frequency are the ones that contribute to the dynamics and to exchanging energy with the cavity mode. And therefore, these negative modes, even if it's a bit weird, they will just not contribute. So everything is just to simplify the math. So then, in such situation, the final interaction Hamiltonian that I wrote, or I don't remember if I finally wrote it, but you have it here now. We can write it in this way, in which essentially we have some tunneling rates that are the same for all the frequencies, and then we have just this integration from -infinity to infinity, and then the single photon tunneling terms, okay? So this is the model that we are going to start from today that describes an open cavity. So it's just one mode of the cavity interacting through this Hamiltonian with the external continuous field that has many frequencies. Okay, so then let's start today with the new part. And in particular, I will start with the Heisenberg picture approach, and I will show you how we can derive an evolution equation that involves only operators of the system, and the environment has already been integrated out in some way. And this is known as the quantum Langevin equation. So let's go for it. So the first thing that we start from is just the Heisenberg equations. So let me write them down. So the Heisenberg equations, so for example, the Heisenberg equation of the intracavity mode, or the annihilation operator of the intracavity mode. This, as you know very well from the previous chapters, this is just the commutator of A with the Hamiltonian that includes the free Hamiltonian and the interaction Hamiltonian, and with an IHR. So then if you just do the commutators, so you will get this equation here, gamma over pi, and then in here we have B of omega. Okay, then you can do the same now for the environment operators. So for the external field operators, and in this case, we just get this equation. Okay, so this is the starting point. So we have the Heisenberg equations, and essentially we want to integrate the equation of the environment and then substitute it in here and find an evolution equation for the system operators. So because we will be actually in this chapter and in the upcoming chapters solving linear equations all the time. So linear equations, you see that this is a linear equation for the variables A or B and so on. I want to show you exactly how this is done in completely general terms. So let me just show you. Imagine that you have an equation that is just x dot equals lambda x plus some function of time. Okay, so I am going to show you how to find a general solution to this kind of equation. And it's very simple. So, I mean, probably you even know it, but just to make sure, I will show you a trick of how to do this very easily. So, in particular, the first thing that you can do is a very simple variable change, in which you define a new variable set that is the exponential of minus lambda t times x, and then the evolution equation of set, so set dot, this is equal to x dot minus lambda x times exponential, okay? And then when you put this equation in here, so you see that this factor here is nothing but f. So then the equation of set is very easy. It's just f of t e to the minus lambda t. Okay? Then this automatically means that the solution for set is just a set at time 0. So we just integrate this equation, set at time 0, and then the integration from t0 to t. So wherever reference time we are taking t0 initially, and then dt prime, and then the exponential of t prime and f of t prime. Okay. Then now we simply come back to the original variable x, and we get the final solution of the equation. And the final solution just looks like this. So x of t will be equal to x of t0, then the exponential of lambda of t minus t0, okay? And then the integration from t0 to t dt prime of the exponential of lambda t minus t prime, and then f of t prime. Okay? So this is the generic solution that you can write down for any linear system in which you have a kind of a linear coefficient, and then you have some kind of forcing, some kind of, we call it driving in optics as we will discuss today, but some kind of forcing that makes the equation inhomogeneous. So essentially, I will be using this kind of solution all the time, so just keep it in mind. And now you know how to do it yourself. So then let me just remove this from here. Let me make it small and bring it around, for example, here. Okay, so then if I use this solution, then I can do the following. So, so as I said, so using this solution, I can essentially integrate the second equation, so the equation for the external modes, and I will find this solution. So the mode of frequency omega at time t, it's equal to the mode of frequency omega at time 0. So this notation here is just a shorthand for, so this is b of omega 0, okay? Then we will get the exponential of this linear coefficient, which is minus I omega in this case. So then we get minus I omega t. And then we have the integration in time of this term in here, okay? So A can be taken as a function that depends on time. So then we get finally this kind. This kind of formal solution, okay? So we call it formal because this is not a full solution of the system, in the sense that what we have done is we have been able to write down the external operators at any time t as a function of the intracavity operators that we care about, okay? However, this actually allows us to now insert this. So if we now insert this solution in the evolution equation of A, then we get the following. So the derivative in time of A, it will be, so we will get the free term. And then we get a couple of interesting things. So the first thing is, so let me see, I will first write down the one corresponding to this. So we have here B of omega, okay? But B of omega has these two contributions, the one at time 0 and the one depending on the intracavity field. So let me write down first that one. So we will have this in here, and then we will get a multiplication of square root of gamma with the square root of gamma, and then the double integration with exponential and so on. I can write it in this way. So we have the gamma over pi, then I write first the time integral with the A operator already here. And now I write all the frequency dependence under the integral in frequencies, but all the frequency dependence, you see that it's contained in this exponential factor here. So this is minus omega t minus t prime. So this is the first factor that we get. And then the second contribution comes from this one in here. So just the initial condition term, and that will give me a minus gamma square root of gamma over pi, then the integration from minus infinity to plus infinity of the omega, and then this exponential of minus omega t minus I omega t with the operator at time 0 for the environment. Okay, so we get these two contributions. And in particular, you see that this one is very easy to simplify because this thing here, as you know very well, this is 2 pi, the delta function of t minus t prime. And at this level, you can already see why we have made the approximations that we have made, or why these approximations simplify everything so much. Because you see a couple of things. First of all, if this would not be minus infinity, okay, this thing in here would not be the delta function. It would be only half of the integration that we need for the delta function. So then we will have to work out a little bit more, and we will do it actually later. So you see exactly how to deal with these kind of situations. And second of all, if the coupling coefficient G would not be independent of the frequency, then we would have it inside of this integral. And again, this, even with the minus infinity, this would not be a delta function. It would be kind of a Fourier transform like of that kind of coupling, okay? So then we will see these kind of extensions later, but you can see already why we did those approximations and why these approximations simplify everything so much. So then this is the equation that we find for the intracavity field, but we can kind of write it in a slightly better way. So in particular, first of all, we have to integrate out the delta function. So we use the delta function to integrate out or to remove the time integral. But note that the limit of integration t is exactly at the boundary defined by or let's say that the condition t prime equal t is exactly at the boundary of the integration domain. And then I need to use the following property of the delta function. So let me write it down. If I'm integrating between tau 0 and tau 1, a function that is continuous and times delta function, and the delta function is defined in the limit, the upper limit, for example, of the integral, then this is not just equal to the function at tau 1, but half of it, okay? And this is something that if you want, in the notes I made a justification of it or an argumentation of why this is the case, just in case you haven't been told this property of the delta function carefully. This also depends on conventions of certain things, but within the context that we are working on, this is actually a correct property. Then we are going to define something very special that will accompany us for a long time, which is called the input operator, bin, which is nothing but this part in here. So this part in here, you see that it's just a Fourier transform of the external operators at time 0, okay? And we are going to give this a name. In particular, we are going to say that minus 1 over square root of 2 pi, that integral, so that Fourier transform. So this object here, that we call it the input operators. okay? And it's just the Fourier transform of t equals 0 and environmental operators, okay? So why do we make this definition? Because actually, once you make the definition, you realize that these operators satisfy the following algebra. So they satisfy this very important algebra, which I write down. Okay. And this algebra is really, really interesting because you see that these are actually canonical commutation relations. But in time. So usually you have always seen canonical commutation relations between operators of a set at equal times, right? But these operators are very special because they satisfy canonical commutation relations in time, meaning that they are a set of harmonic oscillator operators that are labeled by a time index, and they obey a canonical commutation relations with respect to that time index. So this, we will see that this is actually very important because this means that at any time t, okay, we can define some kind of input external operator that it behaves as a harmonic oscillator at that specific time. So at every time this happens. So, but for now it's just a definition, and that it makes the expression or it makes the equation more compact. And then finally with this, we get to write the equation, the evolution equation for the time derivative of A. We can write it in the following way: minus gamma plus I omega c A plus square root of 2 gamma by B in at time t. Okay? So this simple equation is what we call the quantum Langevin equation. Okay? And I note that this is similar to the Heisenberg equation of motion. So we have an equation, evolution equation for the operators, in particular for the annihilation operator, but it has two important contributions. The first one is this gamma in here, that it's minus gamma A, that is damping, okay? So this means that if we would only have that term, the solution of the equation would be that A would be decreasing exponentially with time as e to the minus gamma t, and therefore all the energy would be lost to the environment. So we get a damping term, so we are on the right track because this is what we expect. We expect that if we excite photons inside the cavity, they will be going out of the cavity. But on top of that, we get a term that is kind of a forcing, and I want to just make it a bit more explicit. So this input operator that we get, so this is kind of an external, or it's telling you that the external field acts as a force. Oops. Okay, that, and we say this is the important word in quantum optics, that drives. So it's a driving, an external force driving the cavity. Okay, so we get dissipation, but we also get driving. So, and but it's very important. It's very, very important that you understand that this thing, even though it depends on time, so it depends on at which time you are considering the equation, it is not a dynamical variable. This is not a variable that has its evolution equation and so on, okay? So this is not a dynamical variable. This is not a dynamical variable. And in particular, this is something that is completely fixed. So it's fixed by the initial state of the environment. Okay, so it's something that is given. So if you know what is the initial state of your environment, and I am going to give you now the typical examples that we work with, then you know what are the properties of this input operator, and that's all. You don't need to solve its evolution in time or anything like that. That's only for the operator inside the cavity. And in particular, because this is known, then you see that, and we will see with a specific example, you see that essentially what we are interested in at the end of the day is writing so solving this equation, okay, including more processes that we will add, including intracavity processes, and then we want to solve A as a function of time in terms of explicit time dependence, A at time 0, and then the input operator, so integrations of the input operator. So then that will be a solution, and I will show you in a little bit with one specific example. So, but before we do that, let me discuss this part in a bit more detail. So let me show you what are the properties of this input operator depending on what is the initial state of the environment. And with this, I will show you what is the most general state of the environment that we are going to consider. So first of all, so let me see, yeah. So so let me show you first a few common external states. Okay, and in particular, I am going to show you 3 types of external states, either vacuum, coherent, or thermal. They will always be Gaussian. And I am going to care about what are the statistical properties, okay, of these input operators and so on. So at the end of the day, I am going to care about things such as the expectation value in that state, that external state of the external operators. So for example, this one. Okay, and of course, so, oops, sorry, I wanted to write something slightly different. So what I wanted to say is that we will care about the expectation value of these operators at time 0. Okay. So if the state is pure, if the external state is pure, we can write it always in this way. Okay, so the external operators at time 0, just expectation value with it. If it is a mixed state, then we will just use the mixed state expectation value. But for now, let's focus on this. So what happens if I assume that the external field it's in vacuum? Okay, so I have nothing outside of the cavity, just the vacuum of the electromagnetic field. Then in this case, the external state it's just the vacuum, so it's annihilated by the external annihilation operators, and this I will write symbolically is in this way. So we have the vacuum state, okay? We have the vacuum state for each of the modes of frequency omega. If they would form a discrete set, then the state would just be the tensor product of all the vacua of each frequency omega. This is a continuous set, so then this is just a symbolic notation, okay? It's just a way of telling you you have the vacuum in all the modes. So then this automatically implies that we know what are the statistics at time zero of the external operators. In particular, the expectation value of the operators is zero, the expectation value of the second order moments, it's also zero, okay? And because we are in vacuum, so the second order moments, I mean B times B, then the number, so the B dagger B will also be zero because we are in vacuum. Okay, and then the only non-zero contribution is of course this term B0 of omega, B0 dagger of omega prime, that is a delta function of omega minus omega prime. Okay, and you have two ways of seeing this. The first way of seeing this is that so first of all, if this one is zero, okay, just using the commutation relation between B of omega with B of omega prime, okay, that you know very well in here. So B of omega and B of omega prime, they are a delta function. Then you can just reorder B dagger B as B dagger plus the delta function or minus the delta function. And then essentially you get this expression here. But it's also much more physical because you start from vacuum, you create a photon at frequency omega, and then if you destroy that photon at frequency omega, then you are connecting it to the vacuum state again. But if the frequencies are different, then you create a photon at frequency omega prime, and then you destroy a photon at frequency omega, which is different, so then that will give you zero, okay? So whatever way you look, this is all. And of course, we don't need to consider any other moment, so we don't need third order moments or fourth order moments because the vacuum state is Gaussian. So everything is contained in these first and second order moments. So this is everything that we need to determine the statistical properties, quantum statistical properties of the input operators. And in particular, for the input operator, remember that the input operator is just the Fourier transform of these operators. So we get something very easy. What we get is that the input operator itself has zero first order moment, and then the second order moments are also zero for the combinations that we already wrote in for the frequency dependent operators. So in particular, we have these combinations here. And then again, for the same kind of arguments, we have that this one in here is the only one that is non-zero. Okay? And again, the idea is the same. I already proved that each of these operators, it's an annihilation operator, okay, because they obey a canonical algebra, canonical commutation relations as a function of the label T. And therefore, you can understand this operator as an operator that creates an external photon with label T prime. And therefore, the only way it can be connected to vacuum is by destroying that same photon at the same label T. Okay? So this is the simplest situation. So this is the situation in which now that we know that we are in vacuum, we know the statistical properties, the first and second order moments of the input operators, and then in principle we can come back to this equation, solve A as a function of B in, and then evaluate any moment that we want of A at any 2 times or whatever, using the statistical properties that we have in here. Okay, and this we will do later with some example. But now let me talk about a little bit more complicated external initial states. In particular, the one I am going to talk about is so what happens when we have a coherent. So we have coherent states outside of the cavity, and just to connect with experimental physics, so these coherent states, at the end of the day, they correspond just to lasers. So whenever you take a laser and you send it to the cavity, so you use a laser to drive the cavity. Okay. This is something that I don't think we will get to prove in this course because it's a little bit more advanced, which is the theory of the laser, okay? But you can prove that the field or the state of the field generated by a laser, it's actually a coherent state. I think I already mentioned it as well when studying coherent states, but now you see how important it is. And then this is the situation that we study now. What happens if we don't have vacuum outside the cavity, but we are sending a laser to kind of try to excite the cavity and so on. So then this means that the external field, so the state of the external field in this case, it will not be vacuum anymore, but it will be a displaced vacuum. So this means that we are doing a displacement of amplitude alpha of omega for each of the modes B omega. So I hope you remember the displacement operator from the first long chapter that we studied. Okay, and essentially you see that the only thing that we are doing is it's essentially, so let me write it here in the notation that we used in that chapter. We are essentially doing a displacement, okay, of amplitude alpha of omega for each of the modes at frequency omega, okay? So now we have a coherent state of amplitude alpha of omega at each of the frequencies omega, and we can choose this alpha of omega however we like. So if the laser, for example, is really, really monochromatic, so it has a single frequency and very, very narrow line width, and that's all, then as I will show you with an example, this will just be a delta function of one specific omega, okay? And that's the only one that you are exciting, and anyone else is at zero. But in general, you could think that you have many lasers and that they have a bandwidth and so on, and then you have, in general, you are exciting, in general, modes outside the cavity at frequencies omega. So then essentially in the same kind of symbolic notation, so this means that we have a coherent state in here of amplitude alpha omega for each omega. Okay, but then understanding this, the important thing are the statistical properties of the operators, the first and second order moments, and in particular, the first order moment of the external operators at time zero. Of course, what is the expectation value of the annihilation operator in a coherent state? Because coherent states are an eigenstate of the annihilation operators, so this will just be the corresponding amplitude alpha omega. And the same happens with terms such as B0 omega, B0 omega prime. This is just alpha omega prime, okay? And finally, I write the one of B0 dagger of omega with B0 of omega prime. And this is alpha conjugate of omega, because now we have B dagger and alpha of omega. Okay? So I hope that this is easy to follow from what you remember from coherent states. And therefore, for the input operator, which is just, again, the Fourier transform, and we will write it now explicitly. So the input operator at time t, the first order moment, it will be, so just from the definition, let me just write it down. So the definition was this for the input operator. And then now we simply take the expectation value. And we know that this is alpha of omega. So this is whatever amplitude we are exciting with a laser frequency omega. And then this whole thing, I can call it alpha tilde of t, which is just the Fourier transform of alpha omega, okay? So it's funny because usually you start in time and then you do the Fourier transform and you get something in frequency space. Here we have the opposite. We start with a function that depends on the frequency label, the frequency outside the cavity, and now you make the Fourier transform to bring it to time, okay? So this is the Fourier transform, and therefore finally, we can write this just as alpha tilde of t divided square root of 2 pi. Okay? Okay, so this is for the first order moment. Then if you check the second order moments, so let me also do it for you a bit slowly. So in this case, we get 1 over 2 pi because we have two contributions, and then we have two integrals. So one in omega and t, and the other one in omega prime, for example, and t prime. And then we have the expectation value of B0 of omega and B0 of omega prime. But we have seen already above that this is just alpha of omega times alpha omega prime. So it's separable. So there is no correlation between B0 of omega, B0 of omega prime. And therefore what we get, because they are a multiplication, we just get two Fourier transforms. So one acting on omega and another one acting on omega prime for time t and t prime. So therefore, this is just equal at the end to the first, so to the multiplication of the first order moments, okay? And if you do the same for the B dagger B contribution, so the B dagger B second order moment, then you will see with the same process that this is just again the multiplication of the first order moments. Okay? So this is already interesting because it allows you to think something slightly deep about quantum mechanics, which is that you, as I have said, these input operators, they form also a canonical algebra. So this means that you can either talk about modes with a Fourier or with a frequency label, or you can talk about modes, equivalent modes, with a time label t. And if we call B in, so the expectation value of B in, we call it amplitude alpha in, okay? Then what this is telling you, what these statistics are telling you, is that the state of the external modes, it can also be written equivalently as a coherent state with amplitudes alpha in of t on each of the input operators at time t, okay? So we have a tensor product now over the time label, okay? And if you want, this is kind of a physical picture that is telling you that at every time there is a coherent state outside the cavity that is exciting the cavity, okay? So that comes into the cavity. So this is a very, very interesting physical picture. And sometimes people don't specify so much that these input operators are another time description of the input field. And this is very important for things such as scattering theory, that it's currently very important in modern implementations of quantum optics. So we are combining scattering theory of particle physics with quantum optical settings. Okay, so essentially, this is what we get for the input operator when we have coherent states outside the cavity. And so maybe, yeah, I think I will just do this and then we make a break. So, and then what happens is that sometimes, or most of the time, it's actually a bit annoying to keep all these kind of coherent part of the statistical properties. It's very, very annoying. And then it's much simpler to do a convenient change for the quantum, so at the quantum Langevin equation. Okay, and the convenient change is that instead of talking about the input operator B, we are going to define a new input operator A, in which we have explicitly already discounted the expectation value, okay? So if you want, so we are defining a new operator A in that is just the all B in minus the expectation value of B in. So you will see that this makes us find something very interesting, starting by the fact that this operator, it satisfies vacuum statistics. So you can check that if you just remove the expectation value of B in to B in, the operator that is left, A in, satisfies exactly these statistical properties that are very simple. So everything is zero except for the second order moment B dagger. Okay, in this case, A dagger. So then we will always work with this input operator. In the Langevin equation, the quantum Langevin equation, will be written in this way. So we have that the derivative of T of A, this is equal to the damping part, the free part. And now we get in here a constant term that I will write in a second. And then the contribution of A in. So this constant term A of T, just take a look at the equation itself. So we have here square root of 2 gamma times B in. So when we put in here the expectation value of B in, which is this minus Fourier transform of the frequency amplitudes divided by a square root of 2 pi, this A factor in here, it just looks like this. So A of T, it's equal to minus the square root of gamma over pi and this Fourier transform. Okay? So this is very interesting because you see that at the end of the day, in the equation, injecting a laser from outside the cavity, this is equivalent to some kind of classical forcing. Okay, so we are forcing the cavity mode inside, but with a classical field, with a number, okay, with a function. And then this term in here, it corresponds only to the external quantum vacuum fluctuations. Okay? So, in other words, and this is kind of the final point, in other words, if we add an external coherent or laser driving, so again, this is just lasers, this is completely equivalent to actually writing down a Hamiltonian that it's time dependent, and we call it the driving Hamiltonian, that looks like this. A of t, A minus A of t conjugate, A dagger. Okay, so this is a time dependent Hamiltonian for the intracavity mode. So this is very important because what I am saying is that you have two alternative descriptions. Either you assume that the external modes are in a coherent state, which is a bit annoying because this is a description that depends on external field operators and you want to work with internal field operators, but that's completely equivalent to just assuming that you are, when you send a laser inside the cavity, what you are doing is that you are including a new Hamiltonian in the system, so in the cavity, so it depends on cavity operators. Oops, by the way, this is wrong. So it depends on cavity operators. So this is a Hamiltonian only for the system. And you can assume that outside there is nothing. So you have the vacuum or whatever other state you have, discounting already the lasers, okay? So I will give you one more example, but after the break, and then I show you some example of how to deal with this equation. So let's regroup at 2:05, okay, in 10 minutes. Okay, so what we have seen is this very important fact that having external lasers, like driving the cavity and exciting the external field, it's equivalent to just having a classical force in the evolution equation, the quantum Langevin equation, and this is equivalent to just having a Hamiltonian. Okay, so if you take the commutator of A with this Hamiltonian, you get exactly this, this driving term, okay, for the intracavity field. And this simplifies everything a lot. So you will see many times when you see papers and when you study quantum optics that people just write down this kind of Hamiltonian and they call it driving, and we are using it to describe lasers and so on. So now you know why they can do that. So let me show you one example, because right now it's a little bit dry of what is this A, okay? So let me give you one specific example, which is the one that we always work with, or most of the time in quantum optics, which is what happens when we have just a collection of monochromatic lasers. So imagine that We have a laser that is really monochromatic, so it has perfect frequency definition, and we have many of those at different frequencies. So as I said, this means that outside the cavity, so let me come back to this description. So now when I say that the external modes, okay, are in a coherent state, now what I am saying is that this will be non-zero, these alphas will be non-zero for some specific frequencies. And this can be written just in this way. So alpha of omega is equal to a sum, and let me say from L equal 1 to L. So we have capital L frequency components, and then alpha L, and delta of omega minus omega L. So what I am saying is that we are driving with a certain set of amplitudes omega L with a certain amplitudes alpha L, okay? So then this automatically implies that A of t, so I remind you that A of t is nothing but this kind of Fourier transform of alpha of omega. And the Fourier transform now is trivial because it's just the Fourier transform of delta functions and times this factor, which means that at the end of the day, the A itself can be written in this form. Where in particular the amplitudes, so these driving amplitudes are just related to these amplitudes of the coherent states outside of the cavity. Okay? But this is kind of the important point, that at the end of the day, when we are driving with a periodic, perfectly periodic monochromatic field at frequency omega L, this is equivalent to a force that is periodic as an exponential of minus I omega L t, okay? So you can always use this kind of periodic drivings in order to force the cavity field, and they correspond to external lasers. You just need to have money to buy lasers and to shift the frequencies of the lasers to the frequency that you want, okay? So essentially, this so this is what I want to say about coherent states outside the cavity. And then finally, let me give you one final example that is the most general thing that we will work with, that is thermal states. So what happens? So what happens now when outside the cavity, or the whole system eventually, but outside the cavity, we are at thermal equilibrium at some finite temperature that is not zero, okay? So this means that the external state is now a mixed state that is equal to some normalization factor that we were calling the partition function, if you remember when we studied thermal states. And then we have the exponential of minus the Hamiltonian outside and divided KT, okay? Then you have already, we have studied already what this is, okay? These thermal states and so on. We studied it in this chapter 2. And in particular, if you remember, for thermal states, we still have the property that the average, so the first moment of the thermal state is 0, and also the B of omega. So the BB, second order moment, okay? For omega and omega prime. So on the other hand, the difference with the vacuum state is that now the photon number is not 0. So, and in particular, this is equal to the Bose-Einstein distribution but only if you are evaluating a second order moment for the same frequency, okay? And I remind you that the Bose-Einstein distribution was just this kind of expression here. So the exponential of h bar omega divided kt minus 1 to the minus 1, okay? So this is essentially telling you that all the phase sensitive moments are 0, but the number of photons, okay, or the phase insensitive one, it's proportional, or it's equal to the Bose-Einstein distribution at that specific frequency that you are looking, okay? So nothing really very surprising. However, we can do an approximation that will simplify things. That is the following. So this kind of two frequency correlation or second order moment, we can approximate it by a frequency independent function. Okay, because we know that the Bose-Einstein distribution will be approximately flat in frequency for frequencies that are the cavity minus gamma to the cavity plus gamma, okay? So maybe let me bring here. So essentially you can imagine that the Bose-Einstein distribution, so we are working at optical frequencies, and in order to really see effects in which we see a very large variation in the scale of this around the optical frequency of the cavity, we would need to work at temperatures that are extremely high. And in particular for optical frequencies, the number of excitations, optical excitations at a finite temperature like room temperature, it's essentially 0, it's approximately 0. So even if you work with low frequency oscillators, we just assume that we are working in a region of this Bose-Einstein distribution in which the variation in frequency is not incredibly fast, okay? Which is always what happens in most experiments. So then this is very convenient because now we have here a photon number that doesn't depend on the frequency, okay? And then this simplifies a lot the statistical properties of the input operator. So for example, well, this one is 0, of course, as the same happens for the phase sensitive one of second order. But now, if I want to evaluate the A dagger A for the input operator, so in principle, if I would have here an n depending on omega, I would get a Fourier transform of this n of omega. However, because we are assuming that it's flat, then the final expression is really simple. It's just this thing here. Okay? And let me write down explicitly also the one for the A dagger, which you can either evaluate or just you can find it from the commutator of the previous one, so reordering, and you get n plus 1 delta of t minus t prime. So you see that these two expressions are actually equivalent to these expressions here for vacuum. So when n is equal to 0, so when the number of excitations, of thermal excitations, it's equal to 0, then you recover exactly the vacuum correlations. So the dagger, no dagger is equal to 0 because n is equal to 0, and the no dagger is equal to 1, okay? Or proportional to the delta function, okay? So this is the most general type of environment that we are going to consider. So we are going to consider an environment in which you are allowed to send lasers, so you can use lasers to drive the cavity, and outside you are at thermal equilibrium at some temperature T, okay? So then if I combine everything, and by the way, before I combine everything, maybe I just give you a final remark. So the final remark is, how about the possibility of having some intracavity Hamiltonian? So for example, so H intra is the way I say that you have some processes inside the cavity, like for example, what we have already studied in the previous chapter, like nonlinear dielectrics, or an atom inside the cavity, etc. Okay, so can we just add a Hamiltonian and nothing changes? Because in the model that I have developed, we didn't have anything inside the cavity. The answer is yes, we can do that, but only as long as it's only a small perturbation. So a small perturbation on H0, or if you want, H of the cavity, the free Hamiltonian of the cavity, okay? So, and the reason for this is that I remind you that we have done certain approximations, and in particular, the main approximation we have done, so the main approximations we have done are contained in here, and in particular, we are assuming that only frequencies around the cavity frequency are contributing to the interaction, okay? But for this, we need that omega c is the energy scale that sets the basic energy scale. So this means that the cavity Hamiltonian, okay, is the one that is giving you this frequency omega c. So if you add any other Hamiltonian inside the cavity that really changes a lot these frequencies, then you have to be very careful and you have to go back to this approximation. And now you have to take into account that the frequencies will not be the frequency of the cavity, but the whole transitions of your full Hamiltonian inside the cavity, okay? So this approximation will be broken if the interaction, or not the interaction, like the intracavity Hamiltonian on top of the free Hamiltonian of the cavity is not just a perturbation. So if it's a perturbation, then it's fine because the frequencies or the energy scale, it will still be of order omega c, and you can continue like nothing happened, okay? But otherwise, you have to be very careful. So this is just a side comment in case you ever have to develop a model for an open system with a Hamiltonian that is not just a free Hamiltonian of a harmonic oscillator or something like that. You will have to work a little bit more. And if you are interested in it, I can tell you exactly how to work out some examples. So then if I just assume that this intracavity process are a perturbation, which matches also what we talked about in the previous chapter, we always assume that these are just perturbations in quantum optics, then we get the final form of the quantum Langevin equations, and is the following beautiful one. So we have that the time derivative of the intracavity operator has different contributions. So the first contribution is A of t, then we have minus gamma plus I omega c A, then we have the commutator of any intracavity Hamiltonian that you like, that might even be time dependent. And then finally, we have the contribution of the input operator. So this is the final quantum Langevin equation, and every term has a very specific meaning. So let me just remind you. So this is an external classical drive, so lasers. This is damping. This is a free evolution. So this is any other intracavity processes. And finally, this is the input operator that corresponds to a driving. So it's a quantum driving by the external thermal quantum fluctuations. Okay, so essentially you see that every term has a very good interpretation, and makes this equation actually quite intuitive once you understand it. Okay, this is the final form of the quantum Langevin equation that we will use, and this is a form that you can use now for the rest of your life if you work in quantum optics, or even if you work in any other type of field in which you have harmonic oscillators that are part of an open system. Okay, so we will see now an example of how to solve this equation. And before the example, I just want to make one small remark of something that it's also very intuitive, and we will see with the example very clearly. But it's worth mentioning, that is that the combination of the interplay between dissipation, driving, and interactions, so interactions or intracavity processes, actually all these things, if you wait long enough, they balance. So they reach some kind of equilibrium. So they balance for long times. And therefore, the cavity will relax, so relaxes to some kind of what we call an asymptotic state. Okay, and what's important about this asymptotic state is that it's independent of the initial state. Okay, and you can, so this is actually very intuitive, because whenever you have damping in your system and driving and so on, so whenever you have these kind of processes, what happens is that your system, it will start somewhere, but as you evolve in time, okay, it will reach a new kind of equilibrium. Think, for example, on the simplest example. Imagine that you start with your system in the vacuum state, and the external field is at some temperature. So if you now release your system, okay, from the vacuum state, what will happen? So it will just thermalize. It will just reach the equilibrium temperature, right? So, and that will happen actually if you start in vacuum, if you start in a coherent state, no matter where you start, wherever you start, if you just release the system, it will reach thermal equilibrium again, okay? And it will just lead to a thermal state. And that will be an asymptotic state that doesn't depend on the initial state. Wherever you started from, all that information is washed out, okay? And we will see this with the example. So you might hear other names for this. So sometimes this is called steady state or stationary state. But it's important, I don't want to use these names too much, because whenever you say steady or stationary, it usually means that it's time independent, okay? But that's not what I am saying. So the asymptotic state can still depend on time, and we will see that, for example, in the example we are going to see now, it depends on time, okay? But it's a time dependence that we understand, that we know, and that it's typically periodic or something like this. So it's some kind of asymptotic state that is very well defined, and it's independent of the initial state. That's the most important thing. Okay. So then let me, now that we have all the ingredients that we need to describe open cavities in the Heisenberg picture, let me then consider one specific example and let's study it. So let's consider an empty cavity. So we assume that there are no intracavity processes. So later on in the course, we will study some more complicated situations. And let's also assume that we are driving with a single monochromatic laser. So A of t will be equal to just some amplitude and then a periodic driving. Okay? So this is a single monochromatic laser. So this is the kind of situation we are going to study first. So we are driving an empty cavity, and let's see what is the state that the cavity reaches and so on. And let me do a couple of remarks. So first of all, because the equations of motion are linear, okay, so the quantum Langevin equation is linear because there is no intracavity process, and we start with Gaussian states in the external field. So the initial state is Gaussian, and we have linear equations. Then the state inside the cavity is going to remain Gaussian at all times. So if we start from Gaussian states and we have linear equations of motion, then we will always keep Gaussian states at all times. So this means that we only need to evaluate first and second order moments. To determine the state, and in particular, to determine the Gaussian states. And in particular, as I was saying, we have to determine what we call the mean vector of the Gaussian state, which I remind you is just 2 times the real part of the first order moment in terms of the annihilation operator and the imaginary part of the same. So that's the mean vector of the Gaussian state. And then we have the covariance matrix. And the covariance matrix can be written in terms of moments of the annihilation and creation operators in this way. I think I didn't didn't show you this, but it's something that you can check yourself very easily. And you have it in the notes as well. So we have a contribution to the covariance matrix that comes from the photon number fluctuation. So this is the fluctuation, I remind you, just in case you don't remember, but for any operator, delta A is just A minus the expectation value of A, okay? And then we have another contribution, a bit more complicated, that comes from the phase-sensitive term. So the expectation value of delta A squared, so the phase-sensitive second-order moment, that looks like this. Then here we have the same. So remember that the covariance matrix is symmetric. Okay, so then I write this explicitly just so you see that the only thing we need to evaluate are the first order moment of A, and then the second order moments of A and A dagger, in particular A dagger A and then A squared. Okay, so from this we can determine the state inside the cavity because we know it will be Gaussian. So then let me solve the equation very easily. So in particular, the quantum Langevin equation in this case, it looks just in the following form. So we have this kind of linear term, and then we have the time-dependent forces that include the classical drive and the input quantum operator. And I remind you that we know that the input operator satisfies these statistical properties. And this one. Okay? So from these statistical properties in this equation, it will be very easy to find the solution. And in particular, so this is a linear equation of the same type that I already solved before the break, so at the beginning. And I remind you that the solution of this equation is very simple. You just have to write down the zero time contribution and then an exponential of the linear coefficient, this minus gamma plus I omega c. Times the time, okay? And then we have an integration from 0 to t of dt prime, and now the exponential of, again, the linear coefficient. But now we have the connection between time t and t prime. And then in here we have the whole time-dependent inhomogeneous term of the linear equation. Okay? Now, this A in here is very simple. So we are assuming it's a monochromatic laser. So this is just an exponential of minus I omega t prime, sorry. Of course, all of these are t primes because we are integrating them. And then this automatically means the following. So let me just make a variable change in the integral to simplify things. So I will define tau, that is t minus t prime, so which is the exponent that, so it's the combination that appears in the exponent, okay? And I also define a delta, detuning, which is just the detuning between the laser and the cavity frequency, okay? So we are driving the cavity, but maybe with a frequency that is not exactly the one of the cavity, but any other. Then we get just this final expression, or these final integrals. This is the initial condition term. Then we have here this, and then in here an integration 0 to t d tau e minus gamma minus I delta tau, and finally plus square root of 2 gamma integration 0 to t d tau, and then gamma plus I omega c tau a input operator of t minus tau. Okay, so now this integral, it's trivial to work out. So you know that this integral is just 1 minus the exponential evaluated at time t divided gamma minus I delta, the divided exponent. And therefore, we reach the final solution. And as I said, we are going to be interested in very long times. So we are interested in what is the asymptotic state, so the equilibrium state of the system. And you see that, as promised, this initial condition term will be completely destroyed. Because when you take the time to infinity, in particular when gamma times t goes to infinity, then this exponential goes to 0. And that's independent of what is the initial operator A of 0, okay? If your state is a physical state that is bounded initially, if you wait long enough, it will be completely destroyed by this exponential. So therefore, and of course the same happens for this term in here. So therefore, in the limit, when gamma t goes to infinity, so what we call the asymptotic limit, asymptotic or steady state or stationary state limit, then the final solution is this one in here. So this is the expression that we can use now to evaluate any observable we want from the intracavity field, because we know the statistical properties of this input operator, and this is just some kind of function. So we can evaluate anything we want. So in particular, maybe we do another short break of 10 minutes, and then I give you the final state, okay? Yeah, I think it's better that we do it now, because otherwise it will take me more than another 10 minutes. So let's regroup in 10 minutes. Okay, so we were analyzing the state of an empty cavity that is driven by a laser, a monochromatic laser with the field, external field at thermal equilibrium. And then what we have found is that we can write the annihilation operator at a given time t. In particular, we are interested here in asymptotic times, so very, very long times, can be written in terms of integrals of the input operators, so in terms of the history, okay, the history of the field that has been interacting with it up to that time t, okay? So since we know the statistical properties of the input operator, then now we can evaluate any statistical property that we want of the field inside the cavity. And in particular, we were saying that the field inside the cavity is Gaussian, and because it is Gaussian, we only need to evaluate first and second order moments. So in particular, let me start with the first order moment. So the expectation value of A for long times, this is equal to just taking the expectation value of this expression. Now, this is just a function, so it has expectation value itself, but the expectation value of the input operator is 0. Okay, so then we see that we get exactly this. Okay, now let's evaluate the second order moments, starting by the second order moment of delta A of t squared. And maybe I tell you quickly that, of course, if you check this expression, so you see that this is the full A, but delta A, so if we take the delta A, which is just A minus its expectation value, the only thing that you do is that you cancel this term in here, okay? So delta A is equal to this integral here. So maybe just to make sure, and because today I have some time, we can do it. So let me write down, just as a reminder, that the limit when gamma t goes to infinity of delta A of t, this is equal to just the integration, so the input operator term. So 2 gamma t tau, and then the input operator at time t minus tau. Okay? So using this expression, then it's very simple to see that this second order moment that I am writing here, this is just equal to 2 gamma, and then the limit when t goes to infinity of the integration in t in tau, the integration in tau prime, the exponential of minus gamma plus I omega c, and now we get tau plus tau prime. And finally, we have the expectation value of just the input operators at time t minus tau and at time t minus tau prime. Okay? Now, because this is 0, the whole thing is 0. Okay? Now we can do the same with A dagger A. And we get the same kind of expression, the integration in tau prime, the exponential. But now we have to be a bit more careful because we have A dagger, okay? So A dagger changes the sign of here. Oh, sorry. I realized I made some typo in here. So there is no I factor in front of the gamma. I hope I didn't make you too confused. I think it's okay in this expression, yes. Okay, so because we have to change the I by minus I, then at the end what we get is 2 contributions, one coming from gamma and one coming from omega c, that it's tau minus tau prime. And then in here, we get the expectation value of A dagger input and A input. Okay? Then we have seen that this thing in here for thermal equilibrium, this is equal to just the thermal number of excitations, and then tau minus tau prime. Okay? Then you can use this, this delta function to remove one of the integrations in time, and you finally get an expression that looks like this. So we get 2 gamma n, and then the limit when gamma t goes to infinity of the integration 0 t d tau, and now tau is equal to tau prime, so then the imaginary contribution goes away, and here we get the exponential of minus 2 gamma tau, okay? And if you just perform this integral and you take the limit, this is equal to n. This is not a surprise, right? Like I told you, you should reach thermal equilibrium inside the cavity if you wait long enough. So the number of excitations inside the cavity is just the same number of excitations that we had for the external field, okay? Then if we combine everything, we see that we get a mean value here that is not 0, and we get an a squared that is 0 and a dagger a that is just the thermal number of excitations. So this means that the covariance matrix, so asymptotically, so for long times, the covariance matrix becomes just this covariance matrix. Okay? And what is this corresponding to? So I think I will not surprise you much after the chapter, the long chapter that we did on Gaussian states. So essentially, if I plot here in phase space, so x and p are the position and momentum of the intracavity mode, of the intracavity oscillator, then what we get is something that looks like this. So let me just so first of all, we get here a mean value that is non-zero, and in particular for the position quadrature, we get 2 times the real part of the driving divided gamma minus I delta. And for the momentum, we get 2 times the imaginary part of the same quantity. Okay? And the width of this distribution, so this Gaussian distribution, is just square root of 2n plus 1. And what is this? This is just a displaced thermal state. So this is very, very simple to understand. We have our cavity, and it is in contact with some lasers that are driving it, where one laser that is driving it, and an environment at finite temperature, at equilibrium at some temperature. What happens if we wait? If we wait enough, we will have just that the laser, the coherent part of the field outside the cavity, is creating some mean value inside the cavity, some coherent part of the field inside the cavity that is different than 0, and that it reaches thermal equilibrium. So it has a contribution that it's a thermal state, and it is displaced by the laser field, okay? So now we understand which kind of state do we have. But let me study in a bit more detail the expression for the total photon number. So the total photon number it's very easy to evaluate, so let me call it just n bar, and this is the limit. So I am talking about the asymptotic photon number. So when gamma t goes to infinity of a dagger a, okay? This has two contributions. One is the contribution that simply comes from the absolute value square of the first order moment. And the other is the contribution that comes from the fluctuations. And so in other words, we have a term, so a number of excitations excited by the laser that is given by this, and then a number of excitations that is just excited by the temperature. Then let me rewrite this in the following way. So just to make it simpler to plot now. And for the discussion. So there are many interesting things. So the first, so the thing that I want to discuss in particular is how the photon number inside the cavity depends on the frequency of the laser. Okay. So in particular, you see that it doesn't depend directly on the frequency of the laser only. It depends on the ratio of the frequency of the laser divided the damping in the cavity. So I will represent it normalized to gamma. And then I can plot it, and it looks very simple. So it starts in n. This n is a contribution that is independent of the frequency. And then we have here some function that looks like this. Okay, and this is a Lorentzian. So let me write it down a bit more down. Okay. So this is a distribution that has its center at the cavity frequency, and it has a width that is 1. Okay, so it's the coupling gamma in frequency units, in units of the damping. So and then this is essentially the maximum of the distribution. You see that it's essentially the numerator of this expression plus the thermal photon number. Okay. And then there are many interesting things about this simple expression. So first of all, you can see in here that a laser will only be able to excite photons inside the cavity if the frequency of the laser is inside this range that we discussed of the frequency of the cavity and then the coupling with the environment, okay, above or below. So any frequency that is outside of that interval will not be able to excite that cavity mode. And this actually gives us a kind of a final proof that the approximation that we made, that only modes around the cavity frequency are relevant for the dynamics, it's actually true. So in particular, this shape, it has a Lorentzian shape, which means that only omega L that it's in the interval, approximately in the interval omega c minus gamma, omega c plus gamma, can excite the cavity. So then, as we expected from energy conservation, this is true. So this is the first thing. And then a second thing I want to tell you is that I don't think I will prove it here. Maybe we will do it if we have time. But it's very easy to prove, and you will have it in the notes anyways, that this amplitude epsilon, that we are just using it as a parameter, so we can understand that if the laser is more intense, epsilon will be larger, and if the laser is less intense, it will be smaller. But you can write a specific expression of this epsilon in terms of physical parameters. In particular, you can write down this amplitude of the driving in this way. And this P is the physical parameter that we care about. In particular, this is the power of the laser. So the power of the laser is the knob that you can tune, okay, in the experiment. And power is always energy divided by time, right? So in other words, is how much energy you are sending to the cavity per unit time with your laser. So then this implies that the maximum, so this maximum contribution that we have in this peak, so this epsilon squared divided gamma squared, can be written or can be interpreted. So this is the number of excitations, or the number of photons that we have inside the cavity, okay, because of the laser drive. So the number of photons that we are introducing inside the cavity, and it can be written in this funny way. Is the power divided h bar omega c, and then in here we get a 1/2 gamma, okay? Yeah. So, and then let me interpret this. So first of all, this is energy per unit time, and this is energy per photon, right? Each photon is h bar omega. So then the first quantity that I wrote, this is just the number of photons that we are sending to the cavity per unit time. Okay, the number of photons contained in the laser per unit time. And now this is multiplied by 1 divided 2 gamma. And this is essentially the damping time. So this is how long does it take for a photon inside the cavity to leave the cavity, okay? So it's a measure of that. So this is a damping time. So then if you just do the photons divided by time multiplied by the damping time, this is just the number of photons that can accumulate accumulated, I think accumulated has only one M. English is difficult that way. In a damping, what we can call a damping cycle. Okay? So in the time that one photon leaves the cavity, this is the number of photons that we can send into the cavity. So then this has a very nice interpretation, okay? It's just for you to see that this expression makes sense, okay? It's not something very important, but just so you remember that the number of photons that are left inside the cavity makes perfect sense according to all these arguments. So then you see that just from the number of photons, we can see a lot of interesting stuff, but there is also interesting stuff happening in the field amplitude. So let me just consider also the field amplitude inside the cavity. And when I say the field amplitude, so I mean essentially the full expression of the expectation value of A which is proportional to the expectation value of the electric field inside the cavity. And this will be equal to what? This is equal to, so let me write the driving amplitude, let me write it as some magnitude and some phase. So this is a phi. Okay, and then we can write this expression as the following. So we have the amplitude of epsilon, and then maybe I remind you quickly that this is the expression. So I am going to write the magnitude and the phase explicitly. So you see that the phase of this thing, or the magnitude, is the square root of gamma squared plus delta squared. So I just write it down here. Okay, and then we get in here. So the phase of epsilon, and then the phase of the denominator. So let me write it down. We have here the phase of the driving, so the phase of the laser that we are using to drive the cavity, plus the phase of the denominator, which is just the inverse of the tangent, so the arctan of delta divided by gamma, and then we have also the oscillating exponential. Okay? Then there are a couple of interesting things from this expression that we need to discuss. So the first one is something that a lot of people make a mistake with, that is that you think that because the cavity mode, it's at some frequency that is the cavity frequency, so omega c, the oscillation inside the cavity is at the frequency of the cavity. And that's not true. You can see here that the field oscillates at the laser frequency, not at the cavity frequency. Okay, and this is very important, and if you think about it, it's actually very natural, because you have your oscillator inside the cavity, you are forcing it with some periodic motion, and of course the oscillator is going to start moving at, or let's say that it will, if it has to move, because of this forcing, it will synchronize with that kind of periodic forcing, okay? And also, this shows you why you are not able to excite so well the oscillator when you don't drive, so when you don't force exactly at the frequency of the cavity, because the oscillator wants to oscillate at its own frequency, and you are forcing it at the wrong frequency. So then there is just so much energy that you can transfer efficiently, okay? And in particular, if you have a frequency that is too far away from the cavity frequency, then the oscillator will just not move. It will just say, no, I cannot oscillate at that frequency. I am not allowed. I am inside a cavity that has this resonance frequency, and because it is open, it allows me for a certain bandwidth, but I cannot oscillate at just any random frequency that you want me to, okay? And the second thing that I want to discuss is that actually you see that the field inside the cavity is not exactly in phase with the laser field, okay? In particular, it is in phase with the laser only for when you are driving at resonance. So if you drive exactly at resonance, then the phase inside the cavity is the same as the phase outside the cavity. But if delta is different, so if the frequency of the laser is not exactly the cavity frequency, then they have different phase. And this is very interesting because this means that if you measure the phase inside the cavity Or if you want, what we will measure is actually that the light that comes out of the cavity, you can measure the phase as a function of the laser frequency. This gives you a measure, okay, of precisely the delta, so the cavity frequency. So let me just mention that this allows measuring the cavity frequency. So only when you see that it is in phase with the cavity, so when it is in phase with the laser field, the outside, so the field that is coming out of the cavity is in phase with the field that you are sending in, so with the laser, then you know that you are exactly at the cavity frequency, or equivalently, because the cavity frequency depends on the length of the cavity, then you are measuring the length of the cavity L. And this has a lot of applications. For something that is called high precision measurements. Okay, and for example, this is something that if you have heard about a new field, relatively new field called optomechanics, quantum optomechanics, this is fundamental for this field of quantum optomechanics in order to be able to measure small deviations of the mirror with respect to a certain length of the cavity. So you use this kind of effect, okay? So you see, just from this trivial example, you already get a lot of interesting physics. So this is why I wanted to discuss it in detail. So, but I hope that now you are much more familiar with how you can solve open quantum problems in the Heisenberg picture. And as I said, we will consider maybe a little bit more complicated situations later, maybe even as an exercise. And now to finish,
I have a question.
Oh, amazing! Good. The first question in the course, basically.
This cavity is actually a driven dissipative system. If
yes.
The environment is a laser, right? So
yes.
I think the steady state should not be called equilibrium stage, right?
Yeah. So that's why we call it asymptotic state or steady state or stationary state, and we try to avoid equilibrium. Because in statistical physics, usually you talk about equilibrium state when you talk about this kind of thermal state. Yeah. That is
but what if the environment is in the thermal state, then the steady state for the cavity is a thermal equilibrium state or not?
Then that's very funny, because in that situation you are really reaching the equilibrium state of statistical mechanics. So the exponential of minus the Hamiltonian divided kT. And this you see in here, right? Because if there is no driving, then the cavity is in the thermal state. So in other words, what you are seeing in this chapter is the dynamical theory of how you reach thermal equilibrium. Okay?
Yeah.
So you are essentially saying, I have my system. My system initially is not at equilibrium, it's at some initial state that I put it in the laboratory, but it is connected to a big environment that is at thermal equilibrium. And then I just let it go and I see how it equilibrates at that equilibrium temperature by the interaction with the environment. Okay?
Okay.
So this is the equilibration of a small system towards thermal equilibrium. Okay? Because of the interaction with a bigger system. So if you want, it would be something similar to that you have your gas. Imagine that you have a gas at thermal equilibrium, and now you suddenly take one particle of the gas and you fix it with your, with your finger. You take it and you fix it. And then it's not at thermal equilibrium anymore. It's fixed by whatever external forcing you are doing. But now you release it. And then you study how it relaxes back because all the other particles start thermalizing it, okay?
Oh, yes.
Yeah. So, but you have to be careful because if you are driving the system, this is not a statistical equilibrium state, okay? If you call it equilibrium state, you need to understand that it's dynamical equilibrium. So it's equilibrium because you are balancing your driving with your interactions, with your dissipation, with the temperature, with everything, okay? But this is why we avoid the word equilibrium state.
Also,
So
even if the you mean even if the environment is a thermostat, it's still a German dissipative system.
no, I mean, it's just a dissipative system,
Yeah.
and it reaches a state, an asymptotic state, that happens to be the statistical equilibrium state. You know what I mean?
So in this case, what's its difference between the statistical mechanics? Because in statistical mechanics, the system is also weakly interacting with the environment.
Yes. So statistically, there is no difference. There is exactly the same. Okay. The state is exactly the same, and the only thing I'm saying is that this gives you the dynamics of that process. Okay.
Yeah.
That's the only thing. But you see that that's a particular case. So that's just an example of these more general dynamics that are called non-equilibrium.
Yeah,
Okay.
thank you.
Yeah. Okay. So I'm happy that we have a question. So then let me now give you a couple of final remarks. These you will have in the notes in section 6 of this section 5a. Okay. But I want to introduce it already here for the Heisenberg picture, and later we will do it also for the Schrödinger picture, which is I promise you that at the beginning I told you, okay, what will happen when we have not only a single mode inside the cavity, but we have many modes, okay? And I also consider the situation in which maybe we don't have a single environment, but we have many environments. And I will start from that, and I give you exactly examples of what I mean. So what happens if we have several environments? And what does this mean physically? Okay, for example, in the case of the optical cavity. So imagine, so in our model, so let me just explain it maybe with the figure, it's always easier. So with the sketch. So this is our cavity, okay? And we are assuming that only this mirror is partially transmitting, okay? But we, in general, in an experiment, all mirrors have some finite reflectivity. It's just that some mirrors are very, very, very high reflective, and some other mirrors, we make them a little bit less reflecting on purpose. So we can put things in and out and so on. So then essentially what I am saying is that you could have also this mirror with some partial transmission. And then you will have also the environment on the left. So these are two different environments, one on the right and one on the left. And you can either check the field that is coming out through this one or the field that is coming out through this one. And you can send lasers from this side or from this side. And on top of that, imagine that we have optical elements inside the cavity. Now, when you shine light inside the cavity, because you cannot perfectly align everything and there are borders and so on, it's very easy that part of the light, it scatters in the optical elements and goes out of the cavity through the sides, okay? So you also have an environment in the side of the cavity. So it's an environment that can receive photons because they are not moving in the optical axis, but they go out of the optical axis, okay? So these are environments that are independent. So you have different environments that they are completely independent of each other. If you create an excitation here, you don't create the excitation in here, okay? So what happens when you have such a situation? Then this is what I want to discuss now. And let me just write the example. So imagine that both mirrors are not perfect. So both mirrors are imperfect. Or we are considering the light scattered, the light scattered of the cavity from the side. Okay, so imagine that we are in this situation. Then you can imagine that if all the environments are independent or all of them are weakly coupled and so on, the only difference that you are going to get is the following. So the quantum Langevin equation will still look very similar. So let me write it down and then I discuss the differences. Okay, so the quantum Langevin equation looks like this. And you see that the only apparent difference that you can see is that now you have not a single input operator, but you have one input operator for each environment. And I denote the environments with the label R. And R goes from 1 to capital R. So I use R because usually we call the environment also a reservoir, okay? So anyways, and then what's important here is that the driving amplitude, it will just be a combination, so a sum of all the driving amplitudes of each of the reservoirs or each of the environments. So you can have lasers on each environment, and each of these lasers will just add up. And the same for the damping. The total damping will be the sum of all the dampings. But, and this is important, each input operator is coupled to the intracavity field by its own damping, okay? So in total, the energy escapes at a damping rate sum of all damping rates, but the independent coupling to each input operator is through each independent coupling, okay? And of course, let me maybe give you also the statistical properties of the input operators. As I say, they are independent, so I will only write one of them. For example, this one. So the input operator of environment R at time t with the input operator of environment R prime at time t prime. This is equal to, of course, the thermal photon number, then the delta function of t minus t prime. But now, because they are independent, this will only be non-zero if R is equal to R prime, okay? This is the point. And some people also work with situations in which the environments are not independent, and you could also develop a theory for that. So if you want, you can give it a try to practice. Like you could just assume that you have several environments, not only one, and then proceed as we have done today, and you will find this equation, okay? So then let me consider now the situation of having several modes inside the cavity, okay? Several cavity modes. So let me first write down or plot what we kind of expect from this situation. So imagine that I write here again the photon number inside the cavity, like we have done before. But now I consider a real cavity that has many modes, okay? So of course we have seen already that one of the things that we see is that we have kind of a resonance. We have a resonance at the cavity frequency, so in particular at some cavity frequency omega m. We have a resonance that has a width gamma, so some gamma at that frequency, okay? But what happens if I take the laser and, okay, I put it out of resonance with this frequency, but I keep scanning, so I keep going up. What do you expect? So you expect that at some point, okay, you cannot put light, but at some point, oops, you have again another cavity resonance, okay? And because you have another cavity resonance, you can play the same game, but now maybe the line width is slightly different, okay? Because this is at another frequency. And then the same happens from below. I mean, you can come from below and then you find another resonance. So if this is the case, so this would be the frequency m-1 inside the cavity. And I just remind you that the distance between resonance frequencies, it's something that goes inversely proportional to the optical length or the length of the cavity, L. So if this is the situation, so if the line width, which at the end is the coupling to the environment, is way smaller than the distance between frequencies, so let me write this down. So assuming that the distance between the frequencies is larger than the damping rates or the coupling to the environment, we then get something very simple. That is what you can expect. What we will have is just that each cavity mode, each of them with an annihilation operator, will evolve according to some driving. So whatever lasers we are sending around that cavity frequency, minus then the damping term that it's different for each cavity mode in general. Of course, if the cavity modes are very close, so for example in this situation, because this is still a small number compared to maybe the transmission factor of the mirror, then the variations of the transmission factor of the mirror, then maybe gamma m is still equal to gamma m plus 1 and still equal to gamma m minus 1. But if you go to frequencies that are very far away, so m is very different from m prime, then the gamma m will be different from gamma m prime in general, because you will start seeing the change in the transmissivity of the mirror. So, or the change in the coupling to the environment equivalently. Then we will have in here the Hamiltonian part for any intracavity processes that now might involve the coupling between cavity modes and anything you want. And finally, we will have the coupling to the input operator. And now, and this is the important situation, each of the cavity modes couples to an independent set of input operators. So these input operators satisfy also these kind of correlations. And we are assuming that the input operator of one mode is independent of the input operator of the other mode, okay? This can be done only when you are satisfying this approximation. If these two modes overlap, so if these two Lorentzians overlap, then you cannot do that. You cannot assume that the environment is different for this mode and for this mode. And of course, I think that this is quite a natural question that everyone has when it is presented with this model. because if I tell you that in this cavity there are many modes, all the modes couple to the same external field, right? The external field is only one external field. However, if the frequencies are very different, so in particular, if the frequencies are very different compared to the coupling to the environment, you still can assume that only the frequencies of the environment around that specific cavity resonance will contribute to the interaction with that specific frequency mode, okay? And therefore, at the end of the day, you can still make the approximation that you extend from minus infinity to plus infinity, but in reality, you will be only interacting with a bandwidth that is around the cavity frequency, okay? And for another cavity frequency, those modes around that cavity will not be effectively interacting with the modes of the other resonance, okay? So that is why you can make that kind of approximation, okay? So the external modes that will interact with this frequency are just the modes at those frequencies, okay? And the same happens for this one, and the same happens for this one, even though we still extend the integrations from minus infinity to plus infinity for each of the resonance. So as I said, you can work it out if you want, and you will find these questions very naturally. But essentially, this is all I need you to know, that if we work with many modes, then we will have just this generalization. If we work with many environments, then we will have this generalization. And of course, you can work with both situations, many environments and many modes. And then you just combine both situations, okay? So essentially, this is all I wanted you to know about the Heisenberg picture approach. I hope that now you are kind of big experts in quantum Langevin equations, and now you are ready to solve any open quantum problem with Heisenberg picture formalism. So in the next lecture, what we will do is we will study this problem, but now in the Schrödinger picture, which, as I will argue during the course, it's actually much more useful in general when you want to do research, okay? And then that's actually the kind of problems I always work with Schrödinger picture formalism on open quantum systems. But the Heisenberg picture formalism is very important for many fundamental reasons that you will see. And then in the course, we will still use it because for academic purposes, it's very, very important. So I hope that all this was some interesting new facts for you. And I will then see you next week. So if you have any questions, now is your time. Otherwise, I will just stop the recording and say goodbye.